We're now going to use the instructions we saw before the break and others in several simple I/O program routines. There are two general methods of handling I/O transfers: program data transfers, which involve program loops, and program interrupts. Let's see how program data transfers are implemented in the PDP-11. Program data transfers, the program is structured so that it will cycle or loop until the device is ready. A device is considered ready when data has been read and assembled in the DVR, or when data from the Unibus has been printed or punched, and the DVR can accept new data. At this time, the device either transmits the data or receives the next word or byte from the Unibus. The loop can then be re-entered and the routine repeated. The reason for this loop procedure is the relative speed of the two devices, the CPU and the peripheral. The CPU, as we know, operates at a much faster speed than the peripheral. To compensate for this, the CPU program loops or waits until the peripheral catches up with it. Let's look at a data output or data O operation first. We'll continue to use the teletype interface as our example. In a data O, the data byte is transferred from a memory location specified in the GPR via the Unibus to the printer punch buffer register, or TPB. A flow diagram for a data O transfer to the teletype printer punch is similar to the flow diagram we saw a minute ago. The ready bit of the printer punch CSR is set when the data byte currently in the TPB is printed or punched. The ready bit, when set, indicates that the TPB can accept the next data byte. A new data byte is then moved to the TPB, and the source address is updated. The program now cycles back to the starting point and again checks the ready bit. Keep in mind that this flow is very simplified. Other steps, such as a byte count, would have to be included. Let's see what instructions could be used to implement this little subroutine. The print punch subroutine is assigned a label called punch. A label is a previously identified point in a program. The programmer uses it the same way he would an address. The test byte and branch if positive instructions form a loop that is dependent on the state of the ready bit, bit 7 of the TPS. Until the ready bit is set, the program remains in this little 2-instruction loop. Since the printer punch buffer is empty when the punch subroutine is first entered, the ready bit is already set and the program falls through to the move byte instruction. The move byte instruction retrieves the first byte from a location specified in GPR0 and moves it to the TPB. The ready bit is cleared at this time, and the address in GPR0 is incremented. A branch instruction now returns the program to the starting point at the label punch. The relatively long print punch operation began when the first byte was transferred into the TPB. Until this operation is completed, the ready bit remains clear and the program cycles in the test byte and BPL loop. When the ready bit is finally set, indicating the TPB is again available, we fall through to the move byte instruction and obtain the second data byte from memory. The program continues in this manner, printing data from successive memory locations. Some means of keeping track of the byte count and returning us to the main program would normally be included in a routine of this type. The data path for a data input, or data I, is in the opposite direction. Now, the data byte is transferred from the reader data buffer, or TKB, to a memory location specified in the GPR. The program flow for a data I is similar to the data O flow we just saw. There's one important change, though, the addition of an initial step to start the reader. This step, incidentally, can be eliminated if the data is from the keyboard, not the paper tape reader. With the read operation underway, the program enters a loop to wait for the done bit to be set. This occurs after all the data is read and assembled in the reader data buffer, or TKB. The data is then moved to a memory location and the address is updated in preparation for reading the next data byte. The program now returns to the starting point and the sequence is repeated. The instructions for the reader keyboard subroutine are almost the same as the ones we used in the printer punch subroutine. The reader is directed to read 1 byte from the paper tape when the reader enable bit, bit 0, is set. As you recall, this register is abbreviated TKS. The reader enable bit is set by incrementing the TKS. Our program now loops to a test byte instruction. and a branch if positive instruction until the done bit is set. As soon as it is set, indicating the data has been assembled in the TKB, we fall through to a move byte instruction. The move byte instruction transfers the byte to a memory location whose address is in GPR 0. Notice that the destination address in GPR 0 is auto-incremented. A branch instruction then causes the program to return to the starting point at the label read. The reader enable bit is again set, and the next byte is read to the TKB. As in the printer punch subroutine, some way to return to the main program would also have to be included. Another example of I/O programming is a procedure called data echoing. In data echoing, information from the reader keyboard unit of the teletype is transferred to the printer punch unit. It is a useful procedure that is incorporated in many teletype I/O programs to allow keyboard entries to be printed. The data transfer is by way of the CPU and employs both data I and data O cycles. A look at the program flow shows us that the data echo sequence is a combination of the data out and data in operations we just studied. It begins when the read operation is started at the time the read enable bit is set. This step is unnecessary if data entry is from the keyboard, not the paper tape reader. We first check the done bit to see when the reader or keyboard data is available. Then we check the ready bit in the punch CSR to see if the data can be accepted. After passing through these two loops, the program causes the data to be transferred from the reader keyboard buffer to the printer punch buffer. The data is now printed, and the program branches back to the beginning so that the procedure can be repeated. Remember now, the program shown is abbreviated. Other steps would be required. The instructions for the keyboard echo subroutine should be familiar to you. We've seen all of them before. We begin with an increment TKS instruction. This instruction starts the paper tape reader by setting its reader enable bit 0. The program then loops on test byte and branch if positive instructions until done is set. It then falls through to a second loop. This loop is identical to the first one, except that this time the ready bit controls the operation. At this point, the read data is available in the reader DBR, and the printer DBR is free to accept it. A move byte instruction now transfers the data from one data register to the other. With data in the TPB, a printer punch subroutine begins and the data is printed. In the meantime, the program returns to the beginning of the subroutine at the label echo, and the procedure is repeated when another key is pressed. We've now described how I/O transfers are handled using program data transfers. Now let's see how the other method, program interrupts, is used. Just what is an interrupt anyway? Well, basically, it's a special signal from a peripheral that intervenes in the CPU operation taking place. An interrupt might be used by a peripheral to inform the CPU that an error condition occurred during a read or write operation. In this case, the peripheral is, in effect, saying, "Hey, I know you're busy, but I want to tell you about this parity error I just had." Another use of the interrupt is for a peripheral to tell the CPU when a read has been completed or a write can take place. This application of the interrupt can be put to good use in I/O programming, as we'll see. With a program data transfer, we saw that the CPU waits in a program loop until the peripheral performs some operation. This wait is for a relatively long period, since peripheral devices are notoriously slow in completing their functions. It's a period during which the CPU does nothing. It's wasted time. With the interrupt method of I/O programming, this story is quite different. Instead of waiting while the peripheral does its thing, the CPU can continue with the main program. The time is not wasted. The CPU could possibly address some other peripheral or perform some mathematical computation, almost anything that is not dependent on the first peripheral operation. Then, when the peripheral has completed the read or is ready to write, an interrupt occurs. The interrupt, under priority constraints, stops what the CPU is doing and starts the service routine. The data is then transferred to or from the memory. As you can see, computer time is used much more efficiently. Let's take a look at the highlights of a typical I/O program that uses an interrupt. During execution of the main program, a jump to subroutine instruction causes the CPU to enter a peripheral subroutine. The main program at this time may need data from, for example, paper tape. The subroutine starts the peripheral, which then performs the necessary mechanical operation, in this case, reading data from tape. In the meantime, a return from subroutine instruction takes the CPU back to the main program. The main program then runs concurrently with the reader operation. When the data is completely read and assembled in the DBR, the device interface sends an interrupt to the CPU. The interrupt is the peripheral's way of telling the CPU that the requested data is ready for transmission. The main program is stopped and the CPU enters the interrupt service routine. The vector address, which accompanied the interrupt from the peripheral, points to a memory location that contains the starting address of the service routine. The service routine moves the data to a GPR or memory location where it would be used for some purpose. On completion of the service routine, a return from interrupt instruction returns the CPU to the main program. Let's find out what takes place when the interrupt is asserted by the peripheral. Interrupts do not just happen. The device must first send a request for bus control. The bus request enters the CPU arbitration logic, where its priority level is compared with the processor priority level. The CPU grants bus control to the peripheral if the peripheral priority level is higher than the processor priority level. Now, the device can interrupt the master's operation. As a result of the interrupt, the CPU pushes the current PC and PSW onto the stack. It'll need them again as soon as the interrupt has been serviced. A new PC and PSW are then obtained from a memory location specified by the vector address. The vector address, as you recall, is sent by the peripheral concurrently with the interrupt signal. The new address in the PC is the starting address of the interrupt service routine, which is now executed. Here we see the handshaking between the CPU and the device that leads up to the assertion of the interrupt signal. The sequence begins when the peripheral asserts a bus request or BR. This occurs at the time the done or ready bit is set in the CSR. The CPU receives the BR along with possible BRs from the other devices. The BR levels are compared with the processor priority level, and if our peripheral has the highest priority, the CPU directs the bus grant or BG signal to it. The peripheral responds to the BG signal by setting SAC, or selection acknowledge, and clearing the bus request. SAC, in turn, clears the BG signal in the CPU. At this point, our peripheral does not yet have bus control. It has merely been told it is the next device to get control. Control is not obtained until the device currently using the Unibus completes its data transaction. This is indicated by both the bus busy and slave sync signals being cleared on the Unibus. Now the peripheral asserts bus busy, clears SAC, and the interrupt line is finally raised. With the assertion of bus busy, our peripheral gains control of the Unibus. At the same time the peripheral asserts the interrupt signal, it also defines the vector address on the Unibus data lines. The vector address, we previously learned, is a location that contains the first address of the interrupt service routine. The CPU, in response to the interrupt signal, acknowledges receipt of the vector with slave sync. Slave sync, in turn, clears the interrupt, the data lines, and bus busy. This constitutes release of the Unibus to the CPU. The CPU now clears slave sync and sets bus busy. In the meantime, the PC has been loaded with the first address of the interrupt service routine. The CPU operation now switches to service the interrupt. We're now going to find out how the interrupt is used in I/O programming. Two simple routines that transfer data from the teletype will serve as our example. The first routine is a teletype reader subroutine. This is followed by an interrupt service routine. These two routines are part of a larger program. However, we won't concern ourselves with what the main program does. Our interest is in how the two routines use an interrupt to transfer data. Our program sequence begins with the start of the main program in the PDP-11. The starting address of the program is 1000. Sometime after the main program begins, the CPU requires data from the paper tape reader in the teletype. The CPU directs the teletype reader to read one character and then resumes execution of the main program. A read operation in the teletype is now initiated and we begin to assemble the data in the reader DBR. As soon as the requested data byte is assembled in the DBR, the teletype interface sends an interrupt to the CPU. The interrupt temporarily stops the main program and the data is transferred to the CPU. The main program then resumes where it was interrupted. Let's take another quick look at what our program does. 1. During the main program, a teletype reader subroutine is entered and the tape reader is directed to read one character. 2. The main program resumes while the character is assembled in the DBR. 3. The teletype interface sends an interrupt as soon as the DBR is full. 4. The main program is stopped to service the interrupt and the data is transferred from the DBR to the CPU. The main program resumes when this operation is completed. In writing any I/O program, there are several programming considerations that the programmer is responsible for. First of all, there must be an instruction to set up the stack pointer. This is usually included at the beginning of the main program. Then, the peripheral subroutine must include instructions to load a new PC and PSW into the interrupt vector locations. There should also be an instruction to set certain bits, such as enable and interrupt enable, in the peripheral CSW. Finally, the programmer must write an interrupt service routine that will transfer the data to or from the peripheral. This routine must end with an RTI or RTT instruction so the main program can be re-entered. One of the first things the programmer does is include an instruction to set up or define the stack pointer. Since the stack is going to be used both in the main program and in our reader subroutine, we'll position this instruction at the beginning of the main program. In our example, to set up the stack pointer, we use an instruction that moves 1000 into GPR6. GPR6, as you recall, is normally used as the stack pointer. With 1000 in the stack pointer, the first address to be used in the stack is 776, since the stack pointer is auto-decremented by 2 before an item is pushed onto the hardware stack. When an interrupt occurs, the current contents of the PSW is moved into location 776, and the PC is moved into the next location, 774. The main program begins at address 1000, as we mentioned before, even though this address may appear to you to be the upper stack address. As we can see, this is not the case. Looking at the program layout again, we can see the position of the stack relative to our program. The stack is assigned to that area of memory just before the beginning of the main program. As we noted a little while ago, sometime after the start of the main program, there is a requirement for data from the teletype reader. To obtain the data, the program enters a peripheral subroutine, in this case the teletype read subroutine. Let's find out how we can get from the main program to the subroutine. As the CPU progresses through the main program, it encounters a jump to subroutine or JSR instruction. This instruction directs the CPU to the teletype subroutine which has been assigned the label TTYRD. We'll take a closer look at the JSR instruction in a little while. The teletype reader subroutine begins with several housekeeping instructions that prepare the system for the eventual interrupt. The first 2 instructions load the new PC and PSW into the teletype vector addresses. Following this, we need an instruction that will set 2 bits in the reader CSR, reader enable and interrupt enable. Finally, there must be an instruction that will return the CPU operation to the main program. The instructions that perform these functions are quite simple and straightforward. The first instruction of the subroutine loads the starting address of the interrupt service routine into memory location 60, the teletype interrupt vector address. The identifying label of the subroutine, TTYRD, accompanies the instruction. In our example, we're using 2000 as the starting address of the interrupt service routine. When the interrupt occurs, the peripheral places address 60 on the Unibus data lines. The CPU goes to this address, reads the contents, 2000 in this case, and places it in the PC. Computer operation then continues with the execution of the instruction stored at this new PC address. The next instruction loads a new PSW into memory location 62, the location adjacent to where the new PC is stored. This new PSW is also retrieved by the CPU when the interrupt occurs. The 200 denotes a processor priority level of 4. Consequently, the interrupt service routine will start running at a priority level of 4. The third instruction sets 2 bits in the teletype reader CSR, reader enable and interrupt enable. A move byte instruction transfers the octal quantity 101 into location 177560, the address of the CSR. This causes the teletype to read 1 byte from tape and then allows an interrupt to occur when the byte is assembled in the reader DBR. Back in the main program, we used a JSR, or jump to subroutine instruction, to get us into the reader subroutine. Now, the last instruction of the subroutine is the JSR's companion, the return from subroutine, or RTS instruction. The JSR instruction, shown here at address X, causes the CPU to enter the subroutine at TTYRD. The JSR instruction also saves the old PC, X plus 4, in register R5 so that the CPU can return to its main program. At the conclusion of the subroutine, the RTS instruction returns the CPU to the main program by taking the address in R5 and placing it back in the PC. We'll take another quick look at the reader subroutine instructions before we go on. The routine is located in memory at an address called TTYRD. The first instruction loads the starting address of the interrupt service routine into vector address 60. Then a new PSW is loaded into address 62. The PSW reflects a priority level of 4. This is followed by a move byte instruction that sets the reader enable and interrupt enable bits in the reader CSR. The last instruction is a return from subroutine, which returns the operation to the main program. Let's take a look at where we are with the programming at this time. In the main program, we included an instruction to set up the stack pointer. Then we wrote a short teletype subroutine. Several important housekeeping instructions were included in the subroutine. That leaves us with the interrupt service routine. The interrupt service routine is stored in memory in an area separate from the teletype read subroutine. The purpose of the interrupt service routine is to transfer and use the data byte read by the teletype reader. It is executed as the result of the interrupt being sent to the CPU. The data byte is first transferred from the reader DBR to some storage location, usually a GPR. The data is then tested and manipulated as required. Finally, the interrupt service routine is concluded and the operation returns to the main program. The first instruction in the interrupt service routine is stored in memory at location 2000. The instruction moves the data byte from the teletype DBR to the CPU. Remember now, the fact that the interrupt has occurred indicates that the data is available in the DBR. In our example, a move byte instruction transfers the data from location 177562, the address of the reader DBR, to GPR1. A number of other instructions would now make use of the data in GPR1. The data could be compared with other data or added to data in another location. It could even be output to some other peripheral device, such as a printer. After the required instructions are completed, the interrupt service routine is concluded with a return from interrupt, or RTI instruction. Let's find out what the RTI will do for us. At the time the interrupt occurred, the CPU pushed the current PC and PSW onto the stack. We'll assume that the stack was empty at the time. The PSW contents went to address 776, and the PC went to the next lower address, 774. Then the contents of vector locations 60 and 62 were transferred to the PC and PSW. The interrupt service routine with a starting address of 2000 began and the data was transferred. Now, at the end of the interrupt service routine, the return from interrupt instruction is executed. The RTI pops the previous PC and PSW from the stack, and the main program picks up where it left off. It might be a good idea at this point to run through the entire I/O operation again very briefly. The main program started at address 1000. Sometime after it began, the program had need for data from the paper tape reader in the teletype. To obtain the data, a JSR instruction in the main program caused the CPU to enter a teletype read subroutine. The subroutine began at a memory location with a label of TTYRD. The teletype read subroutine performed several housekeeping steps in preparation for the forthcoming interrupt, and then set 2 bits in the teletype reader CSR, interrupt enable and reader enable. The interrupt enable bit would be used to allow an interrupt to occur when the data became available. The reader enable bit started the read tape operation in the teletype. With the reader operation underway, the subroutine concluded with an RTS instruction and the main program was resumed. The teletype reader then read 1 byte from tape and placed it in the reader DBR. As soon as this happened, the done bit in the reader CSR was set and an interrupt sent to the CPU. The interrupt was accompanied by an interrupt vector of 60 on the data lines. This interrupt vector directs the CPU to the starting address of the interrupt service routine. The starting address of 2000 was then loaded into the PC. A new PSW was also loaded. Program operation then shifted from the main program to the interrupt service routine, which began at address 2000. The interrupt service routine transferred the data byte in the DBR to a GPR. The data was then tested and manipulated as required by the operation. The service routine concluded with an RTI instruction, which returned CPU operation to the main program. At this point, we're going to review a few of the highlights of our discussion on programming peripherals. There are 2 general methods of programming peripheral devices: program data transfers and program interrupts. The teletype print punch subroutine is a good example of a program data transfer. The program waits until the ready bit is set in the printer punch CSR. When the ready bit is set, a byte is moved to the data buffer and the source address, stored in register R0, is auto-incremented. This program loop method, although wasteful of CPU time, is often used. For example, a program loop would be used whenever program continuation is entirely dependent on the data the CPU is waiting for. In the interrupt method of programming, the CPU can proceed with some other operation after starting the peripheral. It does not stop and wait for the peripheral to complete its function. This can result in a considerable saving of computer time. We used a short teletype read subroutine and an interrupt service routine to illustrate the use of a program interrupt. Once the teletype was started, the CPU returned to the main program. When the teletype finally assembled the read data in the DBR, it issued an interrupt to the CPU. The interrupt stopped the main program and started the interrupt service routine. The job of this routine was to transfer the data to the CPU, where it would be put to some use. The sequence concluded with an RTI instruction that returned the CPU to the main program. We'll take another break at this point, and then we'd like you to complete the series of exercises in I/O programming in your workbook. These exercises will help you to better understand the concepts of I/O programming that we've just covered. Please do not begin the second part of this unit until you've finished the exercises and checked your answers against the answer sheets provided in the workbook. When you hear the next tone, turn off this playback unit and proceed to the workbook exercises. After you've completed these exercises, you can continue with this study unit.